Hey guys, this is the first review video for GCSE Chemistry, and this is on particles and atomic structure. So we're going to start with particles and states of matter. That's solids, liquids, and gases. Now on your exam, there's a few things they can ask you about the states of matter, and the first one is to draw diagrams. So for a solid, what you need to make sure you do is all your particles need to be the same size, they need to be in neat rows, and they all need to be touching. If they ask you about the movement of solid particles, you should simply say they are vibrating in place. You don't have to draw the little lines like I did to show that. That's just to remind you that that's how they're moving. For a liquid, they should also be touching. That's the part most students forget. Most of them should be touching. Just make sure they're not in neat rows. So that would be a liquid. They take the shape of their container, and they can move freely past one another. That's one of the main differences between a solid and a liquid. Gases, your last one, should be far apart from each other and random. Make sure your gases don't accidentally end up in neat rows. They're obviously moving freely as well, and they would be moving very fast past each other. The next thing they can ask you about is about the changes of state. So to go from a solid to a liquid to a gas, you need to add energy. That helps to overcome the intermolecular forces of attraction between the particles and separate them into separate molecules or atoms depending on the substance. The first few are really easy. Most of you will remember these from middle school. To change from a solid to a liquid is simply melting, and the reverse from a liquid to a solid, freezing. From a liquid to a gas, boiling. You can change from a liquid to a gas below the boiling point. That's called evaporation. Key things to remember about evaporation are that only the highest energy particles in the liquid will be able to evaporate because the others won't have enough energy to separate from the liquid. The other is that they only separate from the surface. So only particles from the surface escape, whereas boiling, they would all be able to bubble and escape at once. The reverse of that, of course, condensation. We're all familiar with that one. The harder one is solid to gas. You don't encounter as many of these in your daily life, but something you would have seen in chemistry class would be iodine. Iodine changes directly from a solid to a gas, and also dry ice. Solid carbon dioxide does this. So solid straight to gas without passing through liquid is called sublimation. And of course the reverse can occur. That is called deposition. The final thing they often ask about changes of state is for you to write an equation. And it's a lot easier than it sounds. Students often panic about this, but it's really no big deal. If we use that carbon dioxide example, if you were asked to write an equation for the sublimation of carbon dioxide, you would simply write CO2 starts as a solid, and it's still CO2. It's not a chemical reaction, just a physical change. Now a gas. That would be it. Okay. So those are your particle diagrams, and there's your changes of state. The next thing we learned about after states of matter was diffusion. Diffusion happens in fluids, which means it can happen in liquids or gases. The liquids example we did in class was an experiment where you had a beaker filled with water, and we added a drop of food coloring. You could do the same thing with dissolving. You could dissolve a colored salt like potassium permanganate, but if we just add a drop of food coloring, it starts in one place and then spreads slowly. Even if you don't stir, of its own accord, as the particles move, it will spread throughout the liquid, and eventually all of the liquid will be colored. So diffusion is simply particles spreading out. If you take biology, they'll give you a more detailed definition and say it's particles moving from an area of high concentration to an area of low concentration. The idea is eventually it is completely spread through the liquid, and the concentration is the same everywhere. In this experiment, we often do it at a low and high temperature to demonstrate that at a higher temperature, particles move faster. So diffusion would be faster. And you can time how long it takes the food coloring or the colored ions to fully move through the beaker. The other example we do, a little bit more complex, is with gases, and it's using a long glass tube. Hopefully you'll remember seeing a YouTube video of this. And you put 2 bits of cotton, one on either side, containing HCl and NH3. We usually use liquids, use concentrated hydrochloric acid and ammonia solutions. They'll first vaporize, and then the particles will diffuse through the tube. It takes 5 minutes or so. That's not because they're moving slowly. They move quite fast, but there's all these air particles in the way. So they're colliding with the air particles and bouncing back and forth until eventually they move through. When they meet, they react to form a solid. So you have HCl gas and NH3 gas, and together they form ammonium chloride solid, which is white. And that white cloud doesn't form in the middle, interestingly. It forms here toward the HCl. And that's to demonstrate the difference in speeds of diffusion for particles of different mass. So this experiment over here on the left, we were looking at different temperature. This one, we're comparing 2 different masses. HCl is heavier than NH3. So the particles move more slowly. And that is why the cloud forms over here. The NH3 particles were able to make their way all the way here before they met the HCl. All right, so that's diffusion. Next thing we did was pure substances and how to class their particles. So let's draw a few of those. Okay, I'm going to call this atoms, molecules, and compounds. Okay, so for solid liquids and gases, we simply drew each particle as one circle. And that's true if we're talking about something like a noble gas that only goes around as one atom. But many, many substances travel as molecules, or are even compounds where there's more than one type of atom in the sample. So let's do some definitions first, and then we'll draw some pictures of these. So, molecule. A molecule is simply 2 or more atoms bonded together in a small group. All right. I'm going to leave it as just 2 or more, but the key of that small group bit is to remind you if something is giant, if it has billions, we tend to not call it a molecule, we call it giant. Some textbooks will call it macromolecule, but molecule simply means 2 or more atoms. Compound, it's only one different word in the definition. 2 or more elements bonded together. Make sure you can see this. There we go. So they sound so similar. I think it's quite important that we draw a few of these so you can see the distinction. So for molecule, they can be 2 of the same. For example, if this was hydrogen gas, those are hydrogen molecules. But notice they're the same type. It's an element. Elements can be molecules. On the other hand, you could have HCl. And those would also be molecules, even though that is a compound of 2 different elements. For compound, right? We can have, obviously, HCl. Or you could have something much larger. You could have a giant compound like salt. So if this went on and on and on in all directions, this would be a sodium chloride crystal. That's a compound too. Make sure I've got everything. Atom. Atom is a simple one. You're not going to be asked to define an atom, but be aware some substances do travel alone, and those would be the noble gases. So for example, argon would travel as single atoms. Okay. Let's get to the meaty bit now, atomic structure. That's what most of this topic was about. And I think the easiest way to cover atomic structure is by doing an example. So I'm just going to take one from the periodic table. Let's look at boron. Boron has an atomic number of 5 and a relative atomic mass of, I believe, 10.8. So let's look at an atom of boron that has a mass number of 11. That's the most common isotope of boron. The mass number is the larger of the two numbers. So 11 is our mass number. And it is equal to the number of protons plus neutrons. The reason for that, if we make a little table of our 3 subatomic particles, protons, neutrons, and electrons, is that protons and neutrons both have a mass of 1. Electrons have a very, very small mass, almost 0. It's roughly 1/2000th of the others, but very, very small, so it doesn't count toward the mass number. The atomic number on your GCSE periodic tables, they're actually really generous, and they even tell you that this is called the proton number as well, simply because it's the number of protons. So boron would have 5 protons, and if the total of protons and neutrons is 11, it must have 6 neutrons. Neutrons is the one where you have to subtract. So if we were going to draw an atom of boron, we would put 5 protons and 6 neutrons together in the nucleus. The nucleus is at the center of the atom. That's where all the mass is. So the next thing we need to add is our electrons, this third guy here. And to figure that out, we need to look at the charge. Protons have a charge of +1. Neutrons are neutral or 0. And electrons are the ones with a charge of -1. For a neutral atom, the positive charge and negative charge from protons and electrons has to cancel out. So if you have 5 protons, you gotta have 5 electrons. And here they would go. Let's use a different color actually. So 1, 2 fit in your first shell, which means the remaining 3 have to go in the second shell. The second shell can hold up to 8, but we don't need that many spaces, so I'm going to stop at 3. These are called shells. Sometimes they ask you to draw an atom like that. Other times they'll ask you to actually just write the electron configuration. So our electron configuration for boron would simply be 2 in the first shell, comma, 3. That electron configuration actually tells us quite a bit about the atom itself. The 3 here, the number of electrons in the outer shell, tells you the group number. That's where it is on the periodic table. So group number equals the number of electrons in the outer shell. Okay. You can also tell the period number from this. The period number is the number of occupied shells. So we have 2. One shell has 2, one shell has 3. Okay. So for this element, just to recap, the group number would be 3 because there are 3 electrons in the outer shell, and the period number would be 2 because there are 2 shells. 1, 2. Just to remind you, your periodic table, let's have a look here. There's boron, and you can see it is in group number 1, 2, 3. That's what this 3A stands for. And it's in period number 1, 2, the second row. Okay, groups are your columns, periods are your rows. Make sure that's all I wanted to tell you there. Okay, I think we're good so far. The last part of this topic, similar to atoms, is isotopes. All right. So first of all, we need another definition here. Most common mistake on the definition of isotopes is people forget the first word. Isotopes are atoms of the same element with a different mass. So back when I was talking about boron, I said, let's take boron 11. I could have just as easily taken boron 10. This isn't the only way you can get marks for the definition. Sometimes they ask you to define it in terms of subatomic particles, which are these things, proton, neutron, electron. So if we were asked for that, put a big or here, we could say atoms again with the same number of protons but a different number of neutrons. And it accomplishes the same thing. Every element would have its own atomic or proton number, so same element is the same thing as same number of protons. And the only way an element can have a different mass is if it has a different number of neutrons. So these are absolutely equivalent. Just look at the question to help you decide which one they are asking you about. Now, one of the most common things we'll ask you to do with isotopes is work out the relative atomic mass from the periodic table using the isotopic abundance. So if I get this periodic table out again, and let's look at boron, you can see it's not 11 and it's not 10, it's somewhere in between. So the question is, how do we get that number? Well, let's look at, I might as well look at boron. A sample of boron. And in nature, boron is mostly those two isotopes, boron 10 and boron 11. Most of it is boron 11, 80.4%. And the rest, 19.6%, is boron 10. So a question on the exam might give you these figures and then say, calculate its relative atomic mass. Which is another definition for us, RAM. Relative atomic mass, this is the hardest definition of the topic, is the average, so we're going to have to do some math here, the average mass of all the isotopes of an element and then there's this tricky bit at the end, relative to carbon-12. You don't need to go into a lot about why that is. It just has to do with the fact that we've chosen this one here arbitrarily, and in reality, chemists use carbon-12 as their baseline, and we compare everything to that. And what we're really doing is comparing it to a 12th of carbon-12, but you don't need to go into all that at GCSE level. Just remember, that's our standard. All of the others are relative to it. That's where that word relative comes from. All right, so let's solve this guy then. To do a weighted average, we can't just say it's halfway between 10 and 11, so it's 10.5. That doesn't work because most of them weigh 11. Our relative atomic mass has to be closer to 11 than it is to 10. So the way to do that is to simply do the mass times the percent for each one and then add them up. So if I do 10 times 19.6%, but I want to write this as a decimal, because I'm doing this mathematically, so it's 0.196. So that's my boron 10. And then 11 times 0.804 for boron 11. Be really careful when you put that into your calculator. If you don't use the brackets, your answer is going to be all out of whack. And we end up with 10.80. They might ask you something like, does that make sense given the abundances? And you can say yes, because it's much closer to 11 than it is to 10. Another word of warning here is look at the question. If it tells you to write it to 2 decimal places, that means you will literally get a mark for having your answer to 2 decimal places. All right, I think that brings me to the end of particles and atomic structure. Hope you found this helpful, and I'll see you soon for the next video.